After discussing various desirable properties of a best estimator, next our topic is methods of estimation. Here we mainly discuss two methods of estimation. One is methods of maximal likelihood estimation and second is method of least squares. Before we come to the details of method of maximal likelihood estimation, we will discuss a likelihood function. What is meant by likelihood function? Earlier we have found that a probability distribution, maybe probability mass function or probability density function, has two properties. The first property p of xi greater than or equal to 0 and second property summation I is equal to 1 to n p of xi is equal to 1, where x is a discrete random variable assuming values x1, x2, etc. xn. So here we deal with one random variable at a time. That is, x is the random variable. Its values are x1, x2, etc. xn. And this p of xi is defined as probability of x equal to xi. That means the random variable x assumes the value small xi. Its probability is given by this equation. And this function of assigning probabilities to various values of xi is said to be a proper probability mass function if it has the two properties. We considered this property analogous to this discrete random variable in continuous random variable also, and there it is known as probability density function. There we have the positiveness property, that is f of x greater than or equal to 0 and the total probability 1. But note that in both distributions, either in discrete or continuous, we consider only one variable at a time, or it is a univariate probability distribution, one variable at a time. Now we can extend this concept of probability distribution to two variables simultaneously. That is done in bivariate probability distribution. So there may be a lot of situations where we have to consider simultaneous occurrence of two values of a random variable. So if we choose two random variables x and x and y individually have values x1, x2, etc. xm and y1, y2, etc. yn. So if you couple those two random variables to form a bivariate random variable, that is x comma y, this x comma y have values like x1, y1, x1, y2, x1, yn. Next cycle starting in x2, x2, y1, x2, y2, etc. x2, yn. So the values of the random variable, bivariate random variable x comma y are x1, y1, x2, y2, etc. xm, yn. There are mn combinations for x comma y. In a bivariate probability distribution, we deal with the probability distribution of the two random variables simultaneously. That means in bivariate probability distribution, we address probability of x equal to xi, y is equal to yi, and yj, and it is denoted by p of xi yj. So bivariate probability distribution is a simple extension of univariate into a bivariate setup. You can see the equation of univariate as p of xi is equal to probability of x equal to xi. But when we come to bivariate setup, it is extended to joint occurrence of two random variables values together. Here this comma stands for an AND operator, or here we consider joint occurrence of xi to capital X and yj to capital Y. Now this assigning probabilities is said to be a proper probability distribution, proper bivariate probability distribution if it has the two properties, again positiveness property and total probability 1. That is, here individually their values are positive, that is p of xi yj greater than or equal to 0, and this is total of all these mn combinations probability is equal to 1. That is, then we say this p of xi yj is a proper probability distribution. Now we come back to the likelihood function. In likelihood function, we consider again an extension of one random variable to n random variables. That is, likelihood function is a multivariate probability distribution, which means that when we extended that one random variable to two random variable, we get bivariate probability distribution. We can further extend this to k random variables together. That is x equal to x1 equal to x1, x2 equal to x2, x3 is equal to x3, etc. xk is equal to small xk. Here those x1, x2, etc. xk are k random variables, and this k random variables values joint occurrence is considered in that multivariate probability distribution. This multi stands for more than two random variables. So that is a situation of multivariate probability distribution. Again, those multivariate probability distribution will also possess these two properties of positiveness and total probability 1. In likelihood function, this in x1, x2, etc., xn, these are the random variables considered, and these are the random variables actually representing sample. And in likelihood function, this joint occurrence of the values of x1, x2, etc., xn is considered. So multivariate likelihood function is therefore a multivariate probability distribution, and the variables considered in that multivariate probability distribution are the variables representing sample. So if x1 is the variable representing the first unit of the sample, x2 the second unit of the sample, etc., xn is the nth unit of the sample, the probability of x1 equal to small x1, capital X2 is equal to small x2, etc., capital Xn equal to small xn is considered in that multivariate probability distribution or in the likelihood function. Moreover, in bivariate probability distribution, we have a property of independence. That is, if two random variables are independent, then probability of, if two events are independent, we have probability of A intersection B is equal to probability of A into probability of B. When we come to the concept of random variable, this joint occurrence of two values of a random variable, that is given by f of x comma y, bivariate probability is equal to f1x into f2y. That is the case of the two random variables independence. Since in my likelihood function, the variables considered are very randomly chosen, they are independent. Therefore, a joint occurrence probability will be equal to product of individual probabilities, and each variable is drawn from same population. Therefore, the joint occurrence probability will be equal to probability of the first variable fx1 theta, probability of the second is fx2 theta, etc., fxn theta, where fx theta is the population from which the distribution of the population from which the sample has been drawn. This likelihood function is product of n individual density functions. Now, this is illustrated with the help of a sample taken from a Poisson distributed population. Here we have a population following Poisson distribution. From that population, we draw a sample of size 4, and x1, x2, x3, x4 represent the variables drawn to the sample. So this is the likelihood function. Here x1, x2, x3, x4 are drawn from Poisson distributed population. So all these random variables will inherit definitely the population distribution. That's how this likelihood function is product of individual probability density functions. Now, in maximum likelihood estimation procedure, we obtain the estimator of theta, which will maximize the likelihood function. So it's a process of maximizing likelihood function. So which function of x1, x2, etc., xn, or which statistic will maximize the likelihood function, that statistic is known as the maximal likelihood estimator. So by saying this function which maximizes the likelihood function, we cannot get an idea about identifying the function that maximizing the likelihood function. For that, we make use of a device of differential calculus that will maximize a function. In differential calculus, we have method to identify the maximizing point by first derivative equal to 0 and second derivative negative. Therefore, the same procedure is adopted here to find the value of L at which it becomes maximum, value of x1, x2, etc., xn, which makes L maximum. So for that, we have the two equations dl by d theta equal to 0 and d square L by d theta square negative. These two equations are exactly that of borrowed from the differential calculus, the procedure to identify maximum of a function. So in short, maximal likelihood estimator is the equation of x1, x2, etc. xn, or the estimator that will maximize the likelihood function. Now there are certain properties possessed by the maximum likelihood estimators. We have these properties. MLEs are asymptotically unbiased, MLEs are consistent, and MLEs are sufficient if sufficient estimators exist, and also MLEs are asymptotically normally distributed. Even though we have discussed the method of estimation, we are not coming to the real method of estimating parameters based upon samples drawn from different populations. We just discussed the two methods, how to estimate using the two methods. The second method of estimation is method of least squares. This is a method we have already discussed along with the fitting of straight line, parabola, etc. So that device actually used for estimating the parameters, then it becomes a method of estimation method based upon principle of least squares. Here we consider an equation f of x a1 a2 etc ak that followed by these population values. So here a1 a2 ak etc are the constants involved in the equation of these population parameters, or they are treated as the parameters of the population. Then according to the method of least squares, we have suppose an equation f of x a1 a2 etc ak, and if you put x1 here, it is f of x1 a1 a2 etc ak. So this is the value we get theoretically from the equation, and sometimes the value we get theoretically from the equation may be slightly different from the value obtained from the unit. For example, if you are representing x1 or xi as the height and y as the weight, there may be a relation between height and weight. So if a candidate having height x1, we expect the weight according to the equation. Therefore, that x1 is the height, y1 is the weight, but the value given by the equation of weight may be slightly different from the real weight of the candidate. So there is a certain error, and that error is noted by E1. So exactly, so y1 is f of x1, a1, a2, etc. ak, that is the value generated by the equation, plus e1 becomes the real value of the first candidate representing weight. So that epsilon, no, e1 is, or epsilon 1 is denoted as error. According to principle of least squares, the best estimates of a1, a2, etc. ak are those which will minimize this error sum of squares. So error sum of squares is denoted by summation I is equal to 1 to EI square. EI is the difference between the observed value and the expected value. That is yi and f of xi, a1, a2, etc. ak. Therefore, according to principle of least squares, the best estimates of a1, a2, etc. ak are those which will minimize this sum of squares of errors or residues. The same principle is adopted for finding a, b in fitting of a straight line, or a, b, c in fitting of a parabola, etc. So, but for getting these values of a, b or a, b, c in parabola fitting, or a1, a2, etc., ak in this case of estimating parameters, we can make use of a principle of differential calculus for finding the minimum sum of squares. That is given by d by d1 equal to 0, d by da2 equal to 0, d by dak equal to 0, etc. So these equations are known as normal equations. Here the procedure is exactly similar to that of principle of fitting of straight line that we discussed earlier. Here we make use of that principle for estimating parameters. That's how it becomes method of estimation of parameters.